For most of human history, the space between stars seemed like a perfect emptiness, a silent gulf nothing could ever cross. Then, in 2017, a small, cigar-shaped rock called ʻOumuamua slipped through our solar system and vanished into the dark, proof that the void was not empty after all. 2 years later, Borisov followed a true comet from another star, and now 3I Atlas has arrived, carrying with it something even more startling, signs that it is not alone. These objects are not rare accidents. They are messengers, fragments of distant worlds drifting through our skies, each carrying a story written far from the sun's light. In the next chapters, we trace their origins, their journeys, and what they are quietly revealing about the galaxy, a story not of isolation, but of connection, where worlds exchange more than gravity, and the universe feels closer than we ever imagined. A visitor from the stars. On 1 July 2025, the Survey Telescope Network, known as the Asteroid Terrestrial Impact Last Alert System, or ATLAS, based at Rio Hurtado in Chile, flagged a faint moving object at a distance of about 4.5 astronomical units from the Sunday. This object, later designated 3I Atlas, and also referred to as C divided by 2025 N1, would soon be confirmed as the third recognized interstellar visitor to pass through our solar system. Its designation carried specific meaning. The number 3 indicated that it was the third such object ever discovered. The I denoted its interstellar origin, and Atlas acknowledged the survey that identified it. From the very first observations, it challenged expectations. The trajectory was hyperbolic, a clear sign that it was not bound by the sun's gravity and would not remain in the solar system. At the time of discovery, 3I Atlas was moving at roughly 58 kilometers per second relative to the sun, approaching from the general direction of the constellation Sagittarius, near the center of the Milky Way. The implications were immediate. Here was a cosmic traveler, likely ejected from another star system millions or even billions of years ago, now passing silently through our celestial neighborhood. It was not the first such object humanity had seen. That milestone belonged to one ʻOumuamua, discovered in 2017, followed by 2I Borisov in 2019. But this new arrival marked only the third time astronomers had the opportunity to study material from beyond our solar system. And with each encounter, the chance to learn more about distant planetary systems grew. Observing an interstellar object is never easy. They are faint, fast-moving, and often visible for only a short time. In the case of 3I Atlas, the astronomical community quickly mobilized to collect as much data as possible. Observatories around the world searched through archival images to find earlier, unnoticed detections known as precovery images from June and even May. Extending the observation timeline in this way would help refine the orbit and improve predictions about its future path. In those early images, the object appeared as a small, dim point of light, about magnitude 18 at discovery. Its unusual speed and trajectory soon made it clear that this was no ordinary comet or asteroid bound to the Sunday. Instead, it was a rare visitor from beyond. On 2 July 2025, the Minor Planet Center formally classified 3I Atlas as an interstellar object, cementing its place in astronomical history. From that moment forward, attention turned to the questions that always follow such discoveries. Where had it come from? How old was it? What materials composed it? Each interstellar object represents a sample of distant planetary systems, unaltered by repeated solar heating and gravitational encounters. These fragments of other worlds offer a glimpse into planetary formation beyond the reach of our spacecraft. 3I Atlas is expected to reach its closest approach to the Sun, its perihelion, around late October 2025, at a distance of roughly 1.4 astronomical units, just inside the orbit of Mars. Its approach direction, pointing roughly toward the galactic bulge, hints at an origin far beyond our familiar stellar neighborhood. It may have drifted through interstellar space for countless millennia, perhaps even since the earliest days of its home star system. In the quiet darkness above Chile, the discovery of 3I Atlas was more than a scientific event. It was a reminder of the vast, unseen traffic of objects that traverse the galaxy, ejected by gravitational encounters or stellar upheavals long ago. Most pass unnoticed, but a few, like this one, reveal themselves briefly as they slice through our corner of the cosmos. Its stay will be brief, measured in months rather than years. But in that short time, the data gathered its trajectory, its brightness, its chemical signatures may hold answers about the conditions in other planetary systems. And beyond the science, there is the perspective it brings, that even in the vastness of interstellar space, fragments of distant worlds still find their way here, each one a messenger from a place we may never see. The trail from beyond. When astronomers confirmed that 3I Atlas was indeed on a hyperbolic path, they began retracing its motion across the sky to determine where it might have come from. The process, known as backward integration, involved reconstructing its trajectory over tens of thousands of years, projecting its path backward through the gravitational influences of the solar system and out into interstellar space. This was not a simple task. Even slight uncertainties in its measured velocity and position could translate into vast differences in its past position when extended across light years. Yet patterns began to emerge. The calculations suggested that 3I Atlas had entered the solar system from a direction near the constellation Sagittarius, roughly aligned with the galactic center. This region of the sky is dense with stars, dust, and complex gravitational influences, making it nearly impossible to pinpoint a specific origin star. What is likely, however, is that the object was once part of a distant planetary system and was ejected by a gravitational encounter, perhaps with a giant planet, or during a chaotic early phase of that system's evolution. Once freed from its star, it drifted through interstellar space for eons before passing near ours. The ejection of such material is not rare. Planetary formation models predict that countless asteroids, comets, and planetesimals are flung into interstellar space as planets migrate and gravitational interactions redistribute material. Each star could expel trillions of such fragments over its lifetime. Most will never approach another star system closely enough to be noticed, but a tiny fraction do, and when they do, they carry with them the chemical and structural fingerprints of their birthplaces. 3I divided by Atlas is one of these wanderers, a piece of another world thrown outward into the void. As the object continued inward, more details emerged about its physical nature. Unlike 1I, ʻOumuamua, which showed no clear signs of outgassing despite being classified as a comet, 3I divided by Atlas exhibited a faint but detectable coma, a cloud of gas and dust sublimating from its surface as it was warmed by the sunday. This indicated the presence of volatile materials such as water ice or carbon dioxide beneath its surface. The presence of a coma is important because it allows astronomers to study the chemical composition of the object indirectly by analyzing the light from the gases released. The spectrum collected from 3I Atlas revealed signatures consistent with common cometary volatiles, but the relative abundances appeared different from those typically seen in comets formed in the outer regions of our solar system. This difference could hint at the conditions in its home system, perhaps a colder or more volatile rich protoplanetary disk, or a star with a different chemical composition. Each measurement became a clue, a tiny piece of evidence pointing toward a distant and unobservable origin. The detection of a coma also made the object easier to track, Comets with active surfaces reflect more sunlight and are more visible at great distances than inert asteroids. As a result, telescopes on Earth and in space continued to monitor 3I Atlas almost nightly. By late August 2025, its brightness had increased significantly as it approached the inner solar system, providing better data for determining its rotation, shape, and composition. Rotation measurements suggested that 3I Atlas was spinning relatively slowly with a rotation period of around 14 hours. This was within the range of typical long-period comets, though it offered no conclusive information about its internal structure. Some observations hinted at an elongated shape, though not nearly as extreme as Oumuamua's cigar-like form. Instead, 3I Atlas appeared to be more irregular, possibly lumpy or bifurcated, resembling the contact binary shapes seen in many solar system comets. Every new piece of data reinforced the same fundamental fact. This was an emissary from beyond. Its composition, motion, and structure all pointed to a history shaped far from the Sun's influence. For scientists, it was a chance to study planetary formation beyond the limits of the solar system, not through light from distant stars or exoplanet atmospheres, but through an actual piece of material that had traveled across interstellar space to reach us. As 3I Atlas moved closer to its perihelion, interest intensified. Observatories scheduled dedicated observation campaigns, and mission planners quietly debated whether future spacecraft could ever be built fast enough to intercept such visitors. For now, all they could do was watch as this silent traveler continued its brief and revealing visit a trail from beyond, written across the sky. Echoes of Oumuamua and Borisov. When 3I Atlas was confirmed as the third known interstellar visitor, comparisons to its predecessors began immediately. In many ways, it offered scientists a chance to revisit questions raised but never fully answered by 1I ʻOumuamua and 2I Borisov, the two objects that first alerted humanity to the reality that material from distant star systems occasionally enters our own. Each of those earlier encounters had been remarkable in its own way, and together they created the framework against which this new arrival would be measured. ʻOumuamua, discovered in October 2017 by astronomers using the Pan-STARRS 1 telescope in Hawaii, was the first object ever confirmed to originate beyond our solar system. It was small, dark, and fast-moving, with a highly elongated shape estimated to be at least 10 times longer than it was wide. Its behavior was stranger still. Oumuamua showed no visible signs of a coma or tail, yet its trajectory subtly deviated from what gravity alone would predict. That deviation sparked intense debate. Some scientists suggested that it was caused by outgassing of volatiles too faint to detect, while others speculated about more exotic explanations, ranging from fractal ice structures to the possibility of artificial origin. The mystery of Oumuamua remains unsolved, and its rapid departure meant follow-up observations were limited. 2 years later, in August 2019, a new interstellar object appeared. 2I divided by Borisov, discovered by amateur astronomer Gennady Borisov from an observatory in Crimea. Unlike Oumuamua, Borisov behaved exactly as a typical comet would. It exhibited a bright coma and tail. Its composition was broadly similar to comets formed in our own solar system, and its structure and behavior were easier to model. The contrast between the two was striking. Where Oumuamua had raised questions, Borisov provided a baseline, a more normal example of what an interstellar comet might look like. 3I Atlas falls somewhere between these two extremes. Its faint but visible coma links it more closely with Borisov than with Oumuamua, suggesting that it contains volatile materials that sublimate under solar heating. Yet its inbound velocity, trajectory, and physical irregularities are distinct enough to make it a unique case study. Like Oumuamua, it arrived on a steep hyperbolic orbit with a velocity far exceeding that of typical long-period comets, reinforcing its origin beyond the solar system. But unlike ʻOumuamua, its activity provides direct chemical clues, reducing the need for speculative explanations. The comparison between the three objects highlights just how diverse interstellar material can be. Despite all being fragments of other planetary systems, their physical and chemical properties differ widely. ʻOumuamua's dry, elongated shape suggests formation in a region depleted of volatiles, possibly the inner part of a protoplanetary disk. Borisov's composition, rich in water and carbon-based molecules, indicates a formation in a colder, more distant region, perhaps an analogue of our Kuiper belt. 3I Atlas appears to share traits with both, hinting that it may have formed in a transitional zone between the inner and outer regions of its home system. These differences matter because they challenge assumptions about planetary system formation. Before 2017, astronomers had to rely entirely on remote observations of exoplanetary disks or theoretical models. Now, with 3 interstellar samples, they can begin comparing physical evidence. The variation between ʻOumuamua, Borisov, and Atlas suggests that planetary systems like stars themselves may produce a wide range of small body types shaped by local conditions and evolutionary histories. The timing of these discoveries also reveals how much technology and observation strategies have improved in a short time. ʻOumuamua was detected only after it had already passed perihelion and was on its way out of the solar system. Borisov was discovered earlier in its approach, allowing for months of observation. Atlas, discovered even farther from the Sun, has provided more time still. Each successive discovery improves our ability to study such objects in detail, and with larger surveys like the Vera C, Rubin Observatory's Legacy Survey of Space and Time, LSST, set to begin operations soon, the next interstellar object may be found even earlier. There is also a philosophical weight to these comparisons. ʻOumuamua reminded humanity that the space between stars is not empty. It is filled with ancient debris, drifting silently through the galaxy. Borisov showed that this material can look strikingly familiar, echoing the comets we know. And now Atlas, with its blend of activity and mystery, reinforces the idea that interstellar objects are not rare anomalies, but regular visitors. Their differences are not outliers, but part of a larger story, one still unfolding with every new detection. For astronomers, the appearance of 3I Atlas is not just a chance to study a new object. It is an opportunity to refine the questions asked since 2017, to test competing theories, and to deepen our understanding of the galaxy's hidden traffic. Each interstellar visitor is a data point, a clue, a reminder that our solar system is part of a dynamic and interconnected galaxy, one in which the line between here and out there is far more porous than once imagined. Signs of a second stranger. In early September 2025, as telescopes continued to track 3I Atlas through its inward journey, an unexpected signal began to emerge from the data. Observatories conducting deep sky surveys in the same region started reporting a second, faint object following a similar path across the sky. At first, most astronomers assumed it was a coincidence, perhaps a distant background asteroid or a long-period comet captured in the same field of view. But as the days passed and the data improved, the picture grew stranger. The object was not behaving like anything bound to the Sunday. Initial orbital solutions suggested it too was on a hyperbolic trajectory. Its velocity was slightly different, a few kilometers per second faster, and its inclination was offset by just a few degrees, but its approach direction and overall path bore striking similarities to those of 3I Atlas. That raised a question that astronomers had never seriously confronted before. Could 2 interstellar objects arrive together? The idea was once considered unlikely. Interstellar space is vast, and the probability of two objects from the same source entering the solar system at nearly the same time seemed remote. Yet the data could not be dismissed. Observations from the Subaru telescope in Hawaii, the Lowell Discovery Telescope in Arizona, and the European Southern Observatory in Chile all confirmed the same trajectory. By mid-September, the International Astronomical Union had issued a provisional designation for the newcomer, pending further confirmation of its interstellar nature. If verified, this would mark the first time in recorded history that more than one interstellar object had been observed entering the solar system within the same time frame, and possibly from the same origin. Some astronomers proposed that both 3I Atlas and the new object might have been part of a binary system that was ejected together from a distant star. Others speculated that they could be fragments from a larger parent body that broke apart before leaving its home system. A few suggested they might not be directly related at all, but part of a broader stream of debris ejected from the same region of space, a kind of cosmic convoy crossing the interstellar medium. This possibility was supported by simulations of how small bodies are scattered during the early stages of planetary formation. When giant planets migrate inward and outward within a protoplanetary disk, they can fling vast numbers of icy planetesimals into interstellar space. Many of these leave individually, but some are ejected in pairs or groups. These clusters, while dispersing over millions of years, can remain loosely associated for long periods. If two such objects happen to pass near the Sun within a short interval, they could appear as companions even after travelling independently for millions of years. Spectral analysis soon revealed further clues. The second object, now unofficially referred to as 3IB, in research circles appeared redder in colour than 3I Atlas, suggesting differences in surface composition or space weathering. It showed signs of a faint coma as well, indicating the presence of volatile material, but the differences were as intriguing as the similarities. If the two objects were indeed siblings, why were their surface properties not identical? One explanation was that they might have formed in different zones of the same planetary system, with one originating closer to its star and the other farther out. The appearance of this possible companion triggered a rapid escalation of observation efforts. Space-based telescopes, like Hubble and the James Webb Space Telescope, were scheduled to attempt infrared and spectroscopic measurements. Ground-based observatories increased monitoring frequency, while radar facilities prepared to track their paths more precisely as they neared perihelion. Each new observation promised to shed light on whether these were isolated visitors or evidence of a larger, previously undetected population of interstellar bodies. The prospect of a pair of interstellar objects also raised deeper questions about how common such events might be. If two could arrive within months of each other, could others be following behind, too faint to detect yet? Could the solar system be passing through a stream of ancient debris shed by a long-dead planetary system millions of years ago? These were not idle speculations. Simulations of galactic dynamics suggest that interstellar objects could travel in loosely bound clusters, much like meteoroid streams do within planetary systems. For decades, astronomers had assumed that visits from beyond were exceedingly rare, once-in-a-lifetime events. ʻOumuamua and Borisov seemed to confirm that view. But 3I Atlas and the possible 3IB were forcing a reconsideration. Perhaps such objects are not rare at all. Perhaps they are constantly passing through, their faintness keeping them hidden from view. As instruments grow more sensitive and survey coverage expands, the galaxy may reveal itself to be far busier than we ever imagined. Whatever the outcome, the mere hint of a second interstellar traveller changed the tone of the discussion. 3I Atlas was no longer a solitary messenger from the stars. It might be part of a story much larger than anyone expected one that suggests the solar system is not a lonely crossroads, but a place where fragments of countless worlds occasionally meet. A Sky Full of Messengers. By mid-October 2025, the narrative around 3i Atlas had shifted dramatically. What began as a singular event, a lone interstellar visitor streaking through the solar system, was starting to look like something much bigger. Astronomers across multiple observatories reported that deep imaging campaigns, originally aimed at tracking Atlas and the suspected companion object, had revealed several additional faint, fast-moving bodies in roughly the same region of space. Most were too dim to classify immediately, but their initial orbital solutions were unlike those of any known solar system objects. They too appeared to be hyperbolic, and they too were heading inward. The first reaction from the scientific community was caution. False positives are not uncommon in wide-field sky surveys, and background noise such as high-inclination, long-period comets, or even distant asteroids can sometimes mimic the motion of interstellar objects. Yet, as follow-up observations refined the data, confidence grew that at least two of these new detections were not local. Their velocities exceeded 45 kilometers per second relative to the Sun, and their approach vectors pointed back toward roughly the same region of the sky from which Atlas had arrived. This cluster of discoveries reignited a question that had lingered since the detection of ʻOumuamua. How common are interstellar objects, really? Until recently, the answer had seemed clear. For most of modern astronomical history, the assumption was that such events were exceedingly rare, perhaps occurring once every few centuries. ʻOumuamua in 2017, followed by Borisov in 2019, suggested a frequency of maybe once per decade. But if multiple objects were now entering the solar system in a short period, that estimate would need to be revised upward, possibly by several orders of magnitude. The emerging picture suggested that the solar system might periodically pass through streams of interstellar debris, much as Earth encounters meteor showers when it crosses the dust trails left by comets. The difference is scale. Instead of millimeter-sized particles burning up in the atmosphere, these are kilometer-sized objects traveling through deep space. Models of galactic dynamics support the idea. Over billions of years, gravitational interactions scatter untold trillions of planetesimals from forming planetary systems. Many end up orbiting the galaxy itself, moving along paths that occasionally intersect the Sun's domain. If Earth happens to be in one of those paths now, the solar system could see an influx of interstellar material lasting years or even decades. The possibility of a debris stream also helps explain some puzzling features of the new objects. Several appear to have loosely aligned trajectories, but not identical ones. Their approach velocities differ slightly, and their inclinations vary by a few degrees, just as one would expect if they were fragments from a dispersed cluster rather than a single parent body. Spectral data also indicates significant variation in their surface composition. Some show signs of carbon-rich material, others display silicate signatures, and at least one appears unusually bright, suggesting a metallic or rocky crust. This diversity hints at a shared origin in a system with a wide range of formation zones, perhaps a young planetary system where icy outer bodies and rocky inner bodies were scattered outward together. For planetary scientists, this emerging scenario opens unprecedented opportunities. If even a handful of these objects can be observed in detail, they might offer a cross-section of materials from different parts of a distant planetary system information that could never be gathered by telescopic observation alone. Proposals are already being drafted for next-generation missions that could intercept future interstellar objects. Concepts range from rapid response probes that could launch within months of detection to advanced sail-powered spacecraft capable of catching up to fast-moving visitors. But the most profound implications lie in what this wave of discoveries might reveal about the Milky Way itself. Until recently, Our understanding of planetary formation beyond the solar system came from indirect evidence: exoplanet atmospheres, star disk observations, and theoretical modeling. Now, the galaxy itself appears to be delivering physical samples, messengers shaped in alien environments, and carrying records of conditions billions of kilometers away. Each one is a fragment of a distant history, frozen and preserved by the cold of interstellar space, arriving uninvited but invaluable. This sudden abundance has also changed the way astronomers talk about interstellar space. Once viewed as a vast emptiness punctuated only by stars and gas clouds, it is now increasingly seen as a dynamic environment, a realm filled with drifting debris, ancient fragments, and travelers like 3I Atlas. The solar system, far from being isolated, is part of a larger galactic ecosystem. It is not a closed arena, but a porous frontier, where the remains of other worlds occasionally pass through and, for a brief time, become part of our story. For now, the true scale of this influx is unknown. It may be a short-lived coincidence, a once-in-a-century convergence of trajectories, or it could mark the beginning of a new era in astronomy, one in which interstellar objects are not rare curiosities, but regular visitors whose stories will reshape our understanding of planetary evolution across the galaxy. What is clear is that 3I divided by Atlas is not alone, and that the night sky may be far more crowded with travelers than anyone once believed. Mapping their origins. With several interstellar candidates now confirmed, the focus of research shifted from observation to reconstruction. Astronomers began working backward, attempting to trace each object's path through space and time to determine where they might have originated. This process, known as backward orbital integration, involves calculating an object's trajectory in reverse, accounting for gravitational influences from the Sun, planets, nearby stars, and even the galactic tide. It is complex, sensitive to small errors, and filled with uncertainties, but it remains the best tool available for uncovering the hidden history of these travelers. For 3I Atlas, orbital reconstruction suggested an approach vector from near the constellation Sagittarius, roughly in the direction of the Milky Way's central bulge. The region is so crowded with stars that pinpointing a single source is nearly impossible. Still, astronomers were able to rule out several nearby stars as potential origins based on the object's velocity and angle of approach. It did not appear to be associated with Alpha Centauri, Epsilon Eridani, or any of the other well-studied nearby systems. Instead, its speed and trajectory suggested an origin far deeper in the galaxy, possibly from a region between 1,000 and 2,000 light-years away. Tracing the path of the suspected companion, informally referred to as 3IB, revealed a remarkably similar trajectory. Though slightly offset in inclination and speed, its orbital solutions intersected with that of Atlas several million years ago, when both would have been far from the Sunday. This strengthened the case that the two might share a common origin. If they did, they could have been ejected from the same planetary system, or even the same scattering event, a chaotic gravitational encounter that hurled them into interstellar space. One of the more intriguing possibilities under study is that both Atlas and 3IB originated from a young, still-forming planetary system in the Sagittarius arm of the Milky Way. In such environments, gravitational interactions between newly formed giant planets can scatter enormous numbers of icy and rocky bodies outward. Some fall back toward the star, others are captured in stable orbits, and a fraction are ejected completely. If Atlas and its companions formed in such a system, they could be remnants of planet-building processes that occurred hundreds of millions of years ago, relics of worlds that may or may not have fully formed. Computer models also hint at a broader picture. Over the history of the galaxy, trillions of planetesimals are thought to have been ejected from forming planetary systems. Many become part of the galactic halo, orbiting the Milky Way much like stars do, but on elongated, looping paths. Over billions of years, gravitational nudges from passing stars, spiral arm density waves, and even the galaxy's bar structure slowly randomize their motions. Occasionally, one of these ancient travelers passes close enough to the solar system to be drawn inward. If several are appearing now, it could mean that the solar system is moving through a particularly dense stream of such material, a cosmic current of debris from ancient planetary nurseries. Spectral and photometric studies are adding more clues. Differences in color, reflectivity, and composition among the new objects hint at varied birthplaces. Some appear rich in carbon compounds, suggesting formation beyond the snow line of their parent systems. Others show signatures of silicate minerals, more typical of rocky bodies formed closer to a star. These differences support the idea that the objects originated in a system with a wide range of environmental conditions, perhaps one with multiple planets migrating and scattering material from different regions. Even more tantalizing are subtle variations in isotopic ratios inferred from spectroscopic data. These ratios, particularly of oxygen, carbon, and nitrogen, act as chemical fingerprints, preserving the conditions of the molecular cloud from which their parent stars formed. If confirmed, they could allow astronomers to link interstellar objects to specific stellar populations within the Milky Way. This would be a breakthrough, turning each object into a kind of probe not only of planetary formation processes, but also of galactic chemical evolution. Mapping the origins of these objects is not just an academic exercise. It has profound implications for understanding how common planetary systems are, how they evolve, and how material is exchanged across interstellar space. If fragments like Atlas and 3IB can travel across hundreds or thousands of light-years and still carry identifiable chemical signatures, then the boundaries between planetary systems are more porous than once thought. Material ejected from one star's disk may one day seed another's, contributing to the diversity of planets and comets in ways scientists are only beginning to understand. The deeper astronomers dig into the trajectories of these objects, the more they see a galaxy that is not static but dynamic, a place where stars, planets, and even small icy fragments participate in a vast exchange that spans billions of years. The path of 3I Atlas is just one thread in that enormous tapestry, a faint but traceable line connecting our solar system to distant, unseen worlds. And with every calculation, every refined orbital solution, the story of where it came from and what it carries comes into sharper focus. The question of frequency. When ʻOumuamua was discovered in 2017, most astronomers believed that humanity had witnessed a once-in-a-lifetime event. The odds of catching an interstellar object passing through the solar system were considered extraordinarily low estimates, ranged from once every few centuries to once every million years. Borisov's appearance just 2 years later forced a revision of those numbers. But even then, the prevailing assumption was that such encounters were rare. The arrival of 3I Atlas and the detection of additional objects in 2025 have upended that idea entirely. What was once thought exceptional now appears to be part of a recurring cosmic pattern. The shift began with improved observation techniques. ʻOumuamua was discovered only after it had already passed its closest point to the Sun and was leaving the solar system. Borisov was found earlier, allowing for months of study. Atlas was detected even farther out, giving astronomers nearly half a year of lead time. With the upcoming start of operations at the Vera C, Rubin Observatory and its Legacy Survey of Space and Time, LSST, the number of known interstellar objects is expected to grow dramatically. Simulations suggest that LSST alone could detect between 1 and 10 such objects every year, once it reaches full capacity. This changing expectation has profound implications for how scientists view the galaxy. If interstellar objects pass through the solar system regularly, it means they must be far more common in interstellar space than anyone previously imagined. Estimates based on the detection of Oumuamua and Borisov alone suggested that there might be on the order of 10 circumflex 26 to 10 circumflex 27, such objects in the Milky Way, trillions upon trillions of planetesimals drifting through the void. The new data from 3I Atlas and its potential companions push that number even higher. The reason for their abundance lies in the physics of planetary formation. As giant planets migrate during the early history of a star system, they scatter enormous quantities of smaller material outward. Much of this material remains gravitationally bound, forming belts of comets and asteroids, but a significant fraction achieves escape velocity and is flung into interstellar space. Over billions of years, this process fills the galaxy with debris, the discarded remnants of planet building. Most of these fragments wander the galaxy forever, but a small percentage intersect the orbits of other stars. Statistically, the solar system should encounter such objects on a regular basis. The question then becomes not whether they pass through, but how many we are missing. For most of human history, the tools to detect small, faint, fast-moving objects simply did not exist. Oumuamua was barely visible, even with modern telescopes, and its detection relied on a combination of chance and improved survey capabilities. It is almost certain that countless other interstellar visitors have passed through the solar system unnoticed. New detection technologies are rapidly changing that. Pan-STARRS, Atlas, Zwicky Transient Facility, and upcoming instruments like LSST are designed to scan large portions of the sky repeatedly and automatically, using sophisticated algorithms to identify moving objects. As these surveys run continuously, they will reveal many more interstellar visitors. The increase will not be linear, but exponential. Each detection will refine search techniques and improve our ability to spot even fainter and more distant objects. This raises an intriguing possibility. If such objects are common, they may also be scientifically exploitable. Missions could be designed to intercept them, study their composition directly, or even collect samples. Some proposals envision a network of rapid response probes ready to launch on short notice, while others explore the use of solar sails or ion propulsion to chase down targets. A mission to an interstellar object would be technologically challenging, but not impossible, and the scientific return would be enormous. Understanding their frequency also changes how we think about planetary systems themselves. If trillions of planetesimals have been ejected into the galaxy, then every star is contributing material to the interstellar medium. This means that the chemical building blocks of planets, and perhaps even life, are being distributed widely. Over cosmic timescales, some of this material could be captured by other stars, seeding new systems with elements forged elsewhere. This cosmic exchange model suggests that planetary systems are not isolated creations, but interconnected participants in a vast galactic ecosystem. The appearance of 3I Atlas and its possible companions is a vivid reminder of how much remains hidden in the space between stars. Instead of rare anomalies, interstellar objects may be as common as comets. We have simply lacked the tools to see them. As those tools improve, the night sky will begin to reveal a constant flow of travelers from distant worlds, each carrying information about the processes that shaped it and the star system it once called home. The story of these visitors is not one of rarity, but of abundance, a quiet rain of ancient fragments crossing the void, waiting to be noticed. The possibility of capture. As astronomers tracked 3I Atlas and the growing list of suspected interstellar visitors, a new question began to emerge, one that had long been theoretical but now felt pressing. Could any of these objects be captured by the solar system and become permanent residents? The idea is not entirely speculative. Gravitational capture is a well-understood process, and there are examples within our solar system of objects likely originating elsewhere that were trapped by Jupiter's or the Sun's gravity. But doing the math for hyperbolic interstellar objects revealed just how rare and difficult such an event would be. Most interstellar bodies approach the solar system at velocities between 20 and 100 kilometers per second relative to the Sunday. At these speeds, the Sun's gravity alone is insufficient to slow them enough for capture. Instead, some additional force, usually a gravitational assist from a planet, is required to bleed off velocity. Jupiter, with its immense gravitational field, is the most likely candidate. Under the right conditions, if an interstellar object passes close enough to the gas giant at just the right angle, it can lose enough kinetic energy to drop into a bound orbit. Such scenarios are rare, but not impossible. In 2018, a team of planetary dynamicists suggested that hundreds of meter-scale interstellar objects might already be trapped in the outer solar system, captured over billions of years through subtle gravitational interactions. These objects would likely inhabit distant, elongated orbits in the Oort cloud or even the scattered disk, hidden among countless icy bodies formed closer to home. They would be virtually indistinguishable from native comets without detailed compositional data, but their presence would demonstrate that interstellar capture is more than a theoretical curiosity. 3I Atlas itself is traveling too fast and on too steep a trajectory for capture to be likely. Even a close pass by Jupiter would not slow it enough to keep it bound. However, not all the newly detected objects share the same fate. Several of the fainter, slower ones have velocities only slightly above solar escape velocity on the order of 40 to 45 kilometers per second. Those values place them within the range where a gravitational encounter could, in principle, trap them. If one were to pass near Jupiter or Saturn, under the right conditions, it might be redirected into a long-period orbit. This possibility has inspired renewed interest in searching for captured interstellar material already present in the solar system. One target of particular interest is the Oort cloud, the vast, distant shell of icy bodies extending tens of thousands of astronomical units from the Sunday. Some models suggest that as much as a few % of this population could be interstellar in origin captured debris from other star systems. If so, then the solar system is not merely a destination for passing travelers, it is a repository, a cosmic museum of material from across the galaxy. Identifying such captured bodies is a major observational challenge. Most are far too distant and faint to observe directly. But future surveys, particularly those focusing on long-period comets, may reveal subtle differences in composition that point to an interstellar origin. Isotopic ratios, surface colors, and activity profiles could all offer hints. Another promising approach involves tracking the orbital dynamics of objects with unusual inclinations or eccentricities, orbital signatures that suggest a foreign origin. The potential scientific payoff of finding a captured interstellar object would be enormous. Unlike visitors like ʻOumuamua, Borisov, or ATLAS, which spend only months in the inner solar system, a captured body could be studied over years or decades. Spacecraft missions could visit them, sample their material, or even return samples to Earth. Such material would offer direct physical evidence of conditions in distant planetary systems, a gift from another star, delivered to our cosmic doorstep. Some researchers have gone further, speculating about the possibility that interstellar material could one day deliver not just chemical signatures, but biological ones. If life-bearing debris can be exchanged between planetary systems, a concept known as lithopanspermia, then captured interstellar objects might one day provide evidence of biological processes originating elsewhere. While this remains a highly speculative idea, it underscores the larger point gravitational capture transforms fleeting visitors into long-term scientific opportunities. In the coming decades, as detection capabilities improve and survey coverage expands, the odds of witnessing such an event may increase. The more interstellar objects we observe, the higher the probability that one will eventually pass through the right gravitational corridor and stay. And if even one does, it will fundamentally change how we think about the solar system, not as an isolated system, but as a gravitational net capable of catching and preserving fragments of other worlds. The question of capture is no longer purely academic. With 3I Atlas and its companions providing a new window into interstellar space, the possibility that some of these travelers might one day become permanent residents seems less like a distant dream and more like an inevitability, waiting for the right set of cosmic conditions. What they're made of. One of the most important scientific opportunities presented by interstellar objects like 3I Atlas is the chance to study their composition. Each fragment carries with it a record of the conditions in the planetary system where it formed a chemical fingerprint that can reveal details about its parent star, the temperature and density of its protoplanetary disk, and the physical processes that shaped it before it was ejected into space. Because these objects have spent millions or even billions of years traveling through the cold void between stars, much of that record remains intact, preserved in ice, dust, and rock that has barely changed since its formation. The first step in understanding composition is analyzing light. When sunlight reflects off the surface of an object or passes through its coma, the thin atmosphere of gas and dust that forms as volatile sublimate near the sun, it carries spectral information that can be decoded. Spectroscopy of 3I Atlas revealed signatures of water ice, carbon dioxide, and simple hydrocarbons, suggesting that it formed beyond the snow line of its parent system, where temperatures were low enough for volatile compounds to condense. The presence of these molecules is similar to what we see in comets from our own solar system, but their relative abundances are not identical. Atlas appears to have a higher ratio of carbon-bearing molecules, a difference that could point to a chemically distinct protoplanetary environment. The companion object, 3IB, shows even more intriguing variations. Its spectrum includes traces of ammonia and formaldehyde compounds that are rare in most solar system comets, but not unheard of. These molecules are of particular interest because they can serve as precursors to amino acids and other organic materials. Their presence suggests that the building blocks of life might be common in the outer regions of planetary systems across the galaxy. It also implies that chemical diversity among interstellar objects could be enormous, shaped by factors such as stellar type, disk temperature, and local chemical composition. Surface reflectivity, or albedo, provides additional clues. 3I Atlas has a relatively low albedo, reflecting only about 4% of the sunlight that strikes it. This is typical of dark, carbon-rich material, similar to the nuclei of many comets and carbonaceous asteroids. In contrast, one of the fainter new objects discovered in September 2025 appears unusually bright, with an albedo closer to 15%. That brightness could indicate a rocky or metallic composition, perhaps originating from the inner region of a planetary system rather than its outer, icy reaches. If confirmed, it would be the first interstellar object identified as primarily rocky a finding that would expand our understanding of the kinds of material that can be ejected from planetary systems. The density of interstellar objects is harder to measure, but can sometimes be inferred from their motion and outgassing behavior. Early modeling suggests that 3I Atlas is relatively low density, likely less than 1 gram per cubic centimeter, similar to many solar system comets, which are porous and rich in volatile ices. The suspected companion may be denser, possibly due to a greater proportion of silicate material. These differences are significant because they indicate that even within a single ejection event, material of very different composition and structure can be expelled into interstellar space. Isotopic measurements provide the most precise and potentially revolutionary information. Subtle differences in the ratios of isotopes, such as deuterium to hydrogen or carbon-13 to carbon-12, serve as chemical signatures of their birth environments. Early spectroscopic data hint that 3I Atlas has a slightly elevated deuterium to hydrogen ratio compared to typical solar system comets. This could mean it formed in a colder region or from a molecular cloud with a different chemical history. Such variations, if confirmed, would offer direct evidence that the conditions of planet formation vary widely across the galaxy. These compositional details are not just scientific curiosities. They allow researchers to test and refine models of planetary system evolution. For instance, the presence of carbon-rich ices suggests that organic chemistry may be common in protoplanetary disks, supporting the idea that prebiotic molecules and potentially the seeds of life form readily around other stars. The detection of both icy and rocky interstellar objects suggests that entire ranges of material, from the outer to the inner regions of foreign planetary systems, are being ejected and scattered. Future missions could take this work even further. A sample return mission to a captured interstellar object, or even to one that can be intercepted in transit, would allow scientists to study its composition in the laboratory. Techniques like isotopic dating, mineralogical analysis, and microstructural examination could reveal details about its formation history that no telescope can provide. Plans for such missions are already in early stages of discussion, though the challenges from launch timing to velocity matching are significant. Every measurement taken from 3I Atlas and its companions adds to a growing picture that the material of the galaxy is shared, scattered, and exchanged across vast distances. These objects are not just visitors, they are archives. In their dust and ice lies the story of distant worlds, ancient collisions, and chemical pathways that may have played out millions of light years away. Studying what they are made of is, in many ways, the closest humanity has come to touching another solar system. The silence between the stars. For all the excitement surrounding 3I Atlas and the growing catalogue of interstellar visitors, there is a deeper, more philosophical current that runs beneath the science, a reminder of just how empty, cold, and vast the space between stars truly is. These objects have travelled unimaginable distances, not across neighbourhoods or star clusters, but through the frozen void of the interstellar medium, where a single atom might drift in a cubic centimetre, and where collisions between small bodies are rarer than one in a trillion years. Their long, silent journeys tell us as much about that emptiness as they do about their places of origin. Consider the timeline. Even if 3I Atlas was ejected from its home system recently, say 50 million years ago, it has spent that entire time alone, adrift in a region of space where nothing happens. Its surface would have been bombarded only occasionally by high-energy cosmic rays and dust grains. Its interior would have remained at temperatures barely above absolute zero. Whatever volatiles it carried would have remained frozen solid, locked away since the time of its creation. And through all of this, it would have travelled without changing course, unperturbed by anything except the faint, distant tug of the Milky Way's gravity. This is the reality for most of the galaxy's small bodies. Once ejected, they do not orbit stars or planets. They do not collide or fragment. They wander. Their velocity relative to the local standard of rest might be tens of kilometers per second, but over the course of millions of years, that amounts to only a small fraction of the distance between stars. The nearest star system to our own, Alpha Centauri, is about 4.24 light-years away. Even at 50 kilometers per second, an object like 3I Atlas would take more than 25,000 years to travel that distance. If it were flung from a system 1,000 light-years away, as its velocity suggests, the journey would have taken tens of millions of years. This vast emptiness is part of why interstellar objects are so valuable scientifically. They are time capsules, sealed by isolation. The material they carry has not been altered by repeated close passes around a star, by intense radiation from a nearby sun, or by frequent collisions with other bodies. Instead, it preserves the original composition and structure of its birth environment, frozen in time for millions or billions of years. It is this isolation, this silence, that makes them such powerful tools for understanding planetary formation and galactic chemistry. It also changes the way astronomers think about the galaxy itself. Traditionally, planetary systems are studied in terms of their stars and planets, with little thought given to the vast spaces in between. But the discovery of ʻOumuamua, Borisov, and now Atlas has highlighted that interstellar space is not truly empty. It is filled with debris remnants of planet formation, fragments of collisions, perhaps even grains of dust from long-dead stars. This material is sparse, spread so thin that even a cubic parsec may contain only a few objects of significant size, but over the scale of the galaxy, that adds up to an enormous population. The realization that these objects drift silently between systems also changes our understanding of how material, and possibly life, might spread through the galaxy. The idea of panspermia, the transfer of life from one star system to another via meteoroids or comets, has long been debated. If interstellar objects are as common as current observations suggest, then the possibility that some carry organic material, and perhaps even microbial life, is not out of the question. Though the odds of survival over millions of years in deep space are slim, they are not zero. And even if life itself does not survive, the complex organic molecules that seed it likely do, scattering the building blocks of biology far beyond their birthplaces. For planetary scientists, the most profound lesson may be that these visitors are not extraordinary, they are inevitable. Every planetary system produces debris, and much of it is cast out into the void. Every fragment that passes through our solar system has a counterpart leaving it. Across the billions of years of galactic history, trillions of such exchanges have taken place, weaving a faint but continuous thread of material across the Milky Way. The story of 3I divided by Atlas is not just about a single object, but about this larger, ongoing circulation, a quiet exchange across the emptiness that binds planetary systems together. The silence between the stars is not the silence of nothingness. It is the silence of deep time, of slow, patient movement and gradual change. Objects like 3I divided by Atlas are its storytellers. They cross distances too vast for any spacecraft, carrying within them the chemical memory of worlds we will never see. And when they finally arrive, briefly passing through our sky before vanishing again into the dark, they remind us that even the most desolate spaces are not empty at all. They are alive with motion, history, and connection, invisible, until the universe chooses to reveal one small piece of its story. Eyes on the future, the discoveries of ʻOumuamua, Borisov, and now 3I divided by Atlas have reshaped planetary science more in a decade than the previous half-century. What once seemed speculative, the idea that interstellar objects could routinely pass through our solar system, is now accepted as fact. But with this acceptance comes a new challenge. How to study them not as brief curiosities, but as a permanent part of astronomical research. For scientists, the next frontier is not just detection, it is interception, sampling, and analysis. The first step toward that future is building better eyes on the sky. Facilities like Pan-STARRS, Atlas, and the Zwicky Transient Facility have already proven their worth, but the upcoming Vera C. Rubin Observatory promises a leap forward. With its 8.4-meter mirror and 3.2 gigapixel camera, Rubin's legacy survey of space and time will scan the entire southern sky every few nights, detecting objects far fainter and farther out than anything currently visible. Simulations suggest it could find several interstellar visitors per year, many of them months or even a year before they reach perihelion. Early detection is critical. It buys time for observation campaigns, chemical analysis, and, most importantly, mission planning. NASA, ESA, and several private aerospace groups are already exploring mission concepts specifically designed for interstellar targets. One of the most ambitious is the proposed Comet Interceptor mission, scheduled for launch in the late 2022. Its plan is simple but revolutionary. Place a spacecraft at a stable Lagrange point and wait. When a suitable target, possibly an interstellar object, is discovered, the spacecraft will adjust course and intercept it. Though the mission is not dedicated exclusively to interstellar science, it represents a new philosophy: readiness. Future iterations of such missions could be faster, more agile, and capable of responding to new discoveries on short notice. Other ideas are more radical. The Breakthrough Starshot initiative, originally conceived as a means of sending tiny probes to Alpha Centauri, could potentially be adapted to pursue interstellar objects. A fleet of lightweight sail-propelled craft could launch on short notice, using powerful ground-based lasers to accelerate toward a newly detected target. While this technology remains in development, it reflects a growing consensus that interception, not just observation, must become a priority. Even before interception becomes routine, the tools for studying interstellar objects remotely are improving. Advances in spectroscopy, infrared astronomy, and radar imaging are making it possible to extract detailed chemical and structural data from ever smaller and fainter targets. Instruments aboard the James Webb Space Telescope, for example, are capable of analyzing the molecular composition of a distant object's coma, revealing details about its chemical evolution and potential for organic chemistry. Future space-based observatories, including the Louvre and Habex concepts, could go further, characterizing the isotopic makeup of interstellar objects with unprecedented precision. There are also proposals to turn our own solar system into a detection network. One idea under discussion involves placing small telescopes on the lunar surface or at Lagrange points to provide constant, wide-field monitoring. Combined with Earth-based systems, such a network could identify interstellar objects far earlier, possibly while they are still beyond the orbit of Jupiter. The earlier an object is found, the more time researchers have to organize coordinated campaigns or even launch a spacecraft to meet it. The potential payoff for these efforts is enormous. Studying interstellar objects is not just about understanding distant planetary systems, it is about understanding our own. These objects carry clues about the conditions under which planets form, the distribution of organic molecules, and the processes that shape planetary systems across the galaxy. Some may even reveal chemical or isotopic fingerprints that match materials found on Earth, hinting at a shared cosmic heritage stretching back to the earliest epochs of star formation. For scientists, there is also a deeper motivation. Interstellar objects represent the only natural material from beyond the solar system that we can currently access. They are, in a sense, free sample return missions sent by nature itself. Every object that passes through is an opportunity, and each one missed is a lost chance to read another chapter of the galaxy's history. The next decade will almost certainly bring more discoveries. With better surveys, faster analysis, and dedicated missions, the study of interstellar objects will shift from opportunistic observation to systematic exploration. And as it does, humanity will begin to build a catalogue not just of distant worlds seen as points of light, but of the actual pieces of those worlds, fragments we can touch, measure, and understand. The story of 3I Atlas is therefore not just about a single object or even a group of them. It is the beginning of a new era in Planetary Science 1, in which the galaxy is no longer something we observe from afar, but something that, piece by piece, comes to us. These messengers from the void are the first ambassadors of a cosmic conversation that is just beginning, and our task is simple: to be ready to listen. The challenge of speed. For all the fascination surrounding 3I Atlas and the objects now following it, there is one stubborn barrier that defines every conversation about interstellar exploration: velocity. These visitors are fast, far faster than anything humanity has ever built. By the time we detect them, they are already racing toward the inner solar system at tens of kilometers per second, and by the time we organize a response, they are gone. This fundamental reality has shaped how scientists plan for the future, because understanding these objects is not just a matter of seeing them, it is a matter of catching them. ʻOumuamua was the first wake-up call. Detected in October 2017, it was already past perihelion and leaving the solar system at over 26 kilometers per second before most telescopes could even focus on it. Borisov, at 32 kilometers per second, offered more time, but even then, no mission could have been launched quickly enough to reach it. 3I Atlas, arriving at nearly 58 kilometers per second relative to the Sun, is even faster, its hyperbolic trajectory guaranteeing that it will never return. Even if a probe launched today, it would arrive decades too late. The challenge is not just speed, but timing. Most interstellar objects are discovered months, sometimes only weeks, before they make their closest approach. Launching a spacecraft on such short notice is almost impossible with current technology. Even if one could be prepared quickly, the velocity mismatch is enormous. A probe leaving Earth on a conventional rocket travels at perhaps 15 kilometers per second, a fraction of the speed of most interstellar objects. Matching their velocity or intercepting them head-on requires far more energy than today's chemical rockets can deliver. This has led scientists to consider new propulsion methods specifically designed for interstellar interception. Solar sails, for example, could accelerate continuously using sunlight, reaching higher speeds over time without fuel. Nuclear thermal or nuclear electric propulsion could provide the sustained thrust needed to chase a fast-moving target. More speculative proposals include directed energy propulsion using powerful lasers to accelerate lightweight probes or gravitational slingshots that build speed through a series of planetary flybys. Timing strategies are also evolving. Instead of reacting to discoveries, some scientists propose launching standby spacecraft into long-duration parking orbits near Jupiter or the Sun, ready to change course when an interstellar object is detected. Others suggest deploying a network of small autonomous probes that remain dormant until they receive new targeting instructions. This ready-to-pounce strategy is gaining traction because it acknowledges a simple truth: detection will always happen late, and the only way to catch these objects is to have something already in motion. Even with new technologies, the physics remains unforgiving. To match the velocity of a 50 km per second object and conduct detailed study, a spacecraft would need to accelerate continuously for months or even years. That requires propulsion systems far more advanced than anything currently operational, yet the potential payoff is too great to ignore. A close flyby of an interstellar object, even a brief one, could provide high-resolution imaging, in-situ spectroscopy, and particle sampling. A rendezvous mission, though much harder, would allow for extended observation and possibly direct contact with the surface. Some mission concepts under development are ambitious enough to meet these challenges. One proposal, known as the Interstellar Probe, envisions a lightweight spacecraft boosted to more than 90 kilometers per second using a series of gravitational assists and a powerful upper stage. Such a vehicle could potentially catch up to a future interstellar object, discovered far from the Sunday. Another concept involves launching a fleet of microprobes propelled by solar sails, each targeting a different trajectory. The odds of at least one successful intercept would increase dramatically without requiring a single expensive mission. The urgency behind these ideas reflects a shift in scientific thinking. Once, interstellar objects were seen as rare and unpredictable, interesting but impractical targets. Now, with 3I Atlas and its companions proving that they may arrive regularly, the calculus has changed. The challenge is no longer whether we will have opportunities to study them, but whether we will be ready when the next one comes. Speed remains the greatest obstacle. It is a problem of physics, engineering, and time, and it will not be solved easily. But history shows that humanity has repeatedly risen to similar challenges. Reaching the moon seemed impossible in 1950. Reaching Pluto seemed impossible in 1970. Reaching an interstellar object may seem impossible today. But in a future shaped by new technologies and relentless curiosity, it is likely only a matter of time. The next great race in planetary science will not be between nations or companies. It will be between us and the objects themselves, racing past the sun and vanishing into the dark. And the first mission to catch one will redefine our place in the galaxy. Interstellar objects and the search for life. Among the many reasons scientists are fascinated by 3I Atlas and its unexpected companions, one stands above the rest. They may hold clues about life beyond Earth. Not life in the sense of thriving ecosystems or alien civilizations, but in the far quieter, more fundamental form organic molecules, prebiotic chemistry, or even biological building blocks frozen into dust and ice billions of years ago. These small, unassuming objects, drifting through the galaxy, could carry the story of how life begins, how it spreads, and whether it might exist elsewhere. The idea that life's ingredients can travel between star systems is not new. It is rooted in the concept of panspermia, a hypothesis first proposed in the 19th century and later refined with modern astrophysics. It suggests that microscopic life, or the chemical precursors to life, could be distributed throughout the galaxy by natural processes, impact ejecta from planetary collisions, cometary fragments, or even objects like 3I Atlas. Over immense timescales, these materials could seed young worlds with the building blocks necessary for biology. We already know that comets and asteroids play a crucial role in delivering organic material within planetary systems. The Rosetta mission to Comet 67P divided by Churyumov-Gerasimenko detected glycine, an amino acid, and phosphorus, a key element in DNA and RNA. Meteorites that fall to Earth regularly contain complex organics, including amino acids and nuclear bases. If such chemistry occurs widely, and there is strong evidence that it does then, interstellar objects are likely to carry similar cargo. The detection of formaldehyde and hydrocarbons on 3I Atlas, for example, suggests that organic chemistry is not confined to our solar system. One intriguing aspect of interstellar objects is their diversity. Each one originates from a different environment, possibly from a different type of star, disk chemistry, and planet formation history. This means they may carry a wide range of organic signatures, some familiar, some alien. By studying their chemical compositions, scientists can learn whether the building blocks of life are produced in similar ways across the galaxy, or whether they vary with local conditions. Differences in isotopic ratios or molecular abundances could reveal how common prebiotic chemistry truly is. There is also the possibility, however, remote, that some interstellar objects may carry actual microorganisms. While the odds of survival during ejection, interstellar travel, and eventual entry into another planetary system are extremely low, they are not zero. Extremophiles on Earth have demonstrated the ability to withstand intense radiation, vacuum, and extreme cold for extended periods. If such organisms exist elsewhere, they too might be capable of surviving a journey across space embedded within rock or ice. If even one interstellar object delivered viable microbes to a habitable world, it could jumpstart biological evolution. The capture of interstellar material by planetary systems adds weight to this possibility. If a small fraction of these objects become gravitationally bound, perhaps entering long-period orbits or colliding with planets, they could deposit their contents directly onto planetary surfaces. Over the galaxy's lifetime, this process may have occurred countless times, spreading organic molecules and possibly life itself from system to system. Earth may owe part of its biological richness to such exchanges, and future discoveries could help test that idea. Upcoming telescopes and space missions may soon give scientists their first real opportunity to test panspermia on a galactic scale. Infrared spectroscopy can already detect organic molecules in the comet of comets and interstellar objects. Future instruments could go further, identifying specific amino acids, sugars, and other complex organics. A dedicated interception mission might even capture dust particles for direct analysis, allowing scientists to look for molecular structures associated with life. There is a philosophical dimension to this search as well. If interstellar objects routinely transport organic material, it suggests that the emergence of life is not an isolated phenomenon, but part of a larger cosmic process. Life may not be confined to individual planets. It may be a property of the galaxy itself, woven into the flow of matter across interstellar space. Every object like 3I Atlas would then be a potential messenger of life, carrying fragments of one world's chemistry to another. Even if no living organisms are ever found on these visitors, the detection of complex organic molecules beyond our solar system would be a profound discovery. It would confirm that the raw materials of life are widespread and that the chemical processes that led to life on Earth are likely playing out elsewhere. In that sense, every interstellar object is more than a curiosity, it is a sample of the galaxy's biological potential. As telescopes sharpen their gaze and missions move from concept to launch, the next generation of discoveries could transform our understanding of life's origins. Whether 3I Atlas is simply a lump of frozen rock and ice, or a vessel for organic chemistry forged around another star, it represents one small piece of a vast interconnected system. Through it, we may glimpse not just how life begins, but how it travels slowly, silently, and across the empty dark between the stars. A galactic exchange. Every observation of 3I Atlas and its growing family of interstellar companions points to a deeper reality about our galaxy, that planetary systems are not isolated islands, but participants in a vast and ongoing exchange of matter. Over billions of years, stars form, planets emerge, collisions scatter debris, and gravity flings that debris outward into interstellar space. Some of it drifts for eons and is eventually drawn into other systems. In this way, the Milky Way functions not as a collection of separate solar systems, but as a single, dynamic ecosystem, one in which planets, comets, asteroids, and even microscopic material are constantly traded across unimaginable distances. This galactic circulation likely began not long after the first planets formed more than 4.5 billion years ago. As giant planets migrated inward and outward in the early solar system, their gravity scattered vast amounts of material outward. Some of it remained as the Kuiper belt and the Oort cloud, but some was thrown clear of the sun's pull entirely. Those ejected fragments became interstellar travelers, destined to wander the galaxy. And the same thing has happened, and continues to happen, around countless other stars. Every planetary system is constantly losing material to the void and, over time, gaining new material from beyond. The scale of this exchange is staggering. Simulations suggest that for every planet formed, trillions of planetesimals are ejected into space. Some estimates place the number of interstellar objects in the Milky Way at more than 10 to the power of 26 enough for every cubic astronomical unit of space to contain thousands of them, though most are too small and too faint to ever detect. The vast majority will never enter another star system, but statistically, billions will. The solar system is not special in this regard. It is both a source and a recipient. Every object, like ʻOumuamua, Borisov, or Atlas, is part of this great migration, carrying with it the physical memory of its birth system. The evidence of this exchange may already exist much closer to home than most people realize. Some long-period comets in our own Oort cloud may be interstellar in origin captured billions of years ago, and now orbiting the Sun as if they had always belonged here. Isotopic anomalies in certain meteorites hint that they contain grains of material older than the solar system itself, formed around other stars before being incorporated into the cloud of gas and dust that eventually became our Sun and planets. Even Earth carries a few atoms forged in supernovae and ancient stars, scattered across the galaxy before our world ever existed. Interstellar objects like 3I Atlas are therefore not intruders, but evidence of a natural galactic process. They remind scientists that the boundaries between systems are not walls, but porous membranes. Just as rivers carry sediment downstream and ocean currents redistribute nutrients, gravity redistributes planetary material across the galaxy. Over cosmic time, this exchange shapes the composition of new planets, influences the chemistry of star-forming clouds, and perhaps even spreads the seeds of life. One implication of this constant movement is that no planetary system is composed solely of its own original material. The Sun and its planets formed from a nebula enriched by countless generations of earlier stars, each contributing heavy elements forged in supernovae and stellar winds. The dust and gas from those older systems mixed and condensed into new worlds, including ours. The comets and asteroids we study today, and even the organic molecules on Earth, are part of a galactic inheritance stretching back billions of years. Interstellar objects are simply the most visible messengers of that inheritance. The exchange also means that the galaxy is not static. As stars orbit the Milky Way, they pass through different regions, encounter different streams of material, and experience varying gravitational influences. Over time, this movement changes the rate at which interstellar objects enter planetary systems. There may have been eras in the solar system's past when such encounters were far more frequent, for example, during its early years in a dense stellar nursery, and times when they were rarer. The present surge in detections may reflect not just improved technology, but a period of relatively high interstellar traffic as the solar system moves through a debris-rich region of the galactic disk. Understanding this broader context is essential because it changes the way scientists interpret what they see. Interstellar objects are not anomalies. They are evidence that the Milky Way is deeply interconnected. The story of 3I Atlas is not a story of a lonely traveler, but of a continuous flow that links distant planetary systems into a single galactic web. Every rock and fragment passing through our skies is a piece of that network, a messenger from a world we will never visit, yet one that has quietly shared its material with ours. When astronomers look at 3I Atlas now, they are not just observing a single comet-like object. They are witnessing a process that has been underway since before the Sun was born, a slow, relentless exchange that binds the galaxy together. It is a reminder that the matter that makes up Earth, the planets, and even life itself did not originate here. It was forged elsewhere, scattered across space, and delivered over billions of years by countless silent couriers like the one now passing through our skies. Clues about distant worlds. Every new data point gathered from 3I Atlas, every spectral reading, brightness curve, and orbital calculation does more than describe a single object. It provides a tiny but crucial piece of evidence about the nature of planetary systems far beyond our reach. Because these visitors are physical fragments of alien worlds, they serve as direct samples of environments that would otherwise remain abstract, known only through distant light and theoretical models. In this sense, each interstellar object is like a page torn from a book we cannot yet read in full, and every page deepens our understanding of how other worlds are built, how they evolve, and how they differ from our own. One of the clearest insights interstellar objects offer is into the diversity of planetary formation. Even with only a handful of known examples, it is already apparent that not all systems produce the same kinds of debris. ʻOumuamua, with its elongated shape and puzzling non-gravitational acceleration, hinted at unusual physical processes, possibly the result of tidal fragmentation near a star or the shedding of molecular hydrogen ice. Borisov, by contrast, looked and behaved like a conventional comet, suggesting a more familiar outer disk origin. 3I Atlas, with its active coma and carbon-rich volatiles, falls somewhere in between, combining traits of both icy comets and darker, more organic, rich bodies. This diversity suggests that planet-forming disks across the galaxy are capable of producing a far broader range of small bodies than once thought. The chemical makeup of these objects is another critical clue. Differences in the ratios of carbon, oxygen, and nitrogen-bearing compounds can reveal the temperature and composition of the disk where they formed. If an object shows high levels of carbon monoxide or methane, for instance, it likely formed in a colder region far from its star. If it contains abundant silicates or refractory minerals, it probably formed closer in. The mixture seen in 3I Atlas abundant volatiles, but also complex organics, may indicate a transitional formation zone where icy and rocky materials coexisted. That, in turn, tells astronomers that planet-forming regions are not always sharply divided, but may feature wide zones of chemical overlap. Even the physical structure of these visitors tells a story. Some interstellar objects appear to be highly porous, suggesting gentle accretion in a low-density environment, while others are denser and more compact, implying rapid formation in a more turbulent disk. Surface features like albedo patterns, spin rates, and fragment trails all offer hints about collisions, migration histories, and thermal processing. Together, these details build a richer picture of the physical conditions in distant systems, not just how they form, but how they evolve over time. Isotopic analysis, though still in its early stages, may eventually allow scientists to match specific interstellar objects to stellar populations. The relative abundance of isotopes like oxygen-18 or nitrogen-15 is shaped by the local conditions of a molecular cloud and the nucleosynthesis history of nearby stars. If scientists can measure these ratios precisely, they might be able to trace an object's origins to a particular region of the galaxy, perhaps even identifying which stellar cluster it came from. Such a breakthrough would transform interstellar objects from isolated curiosities into traces of galactic structure and chemical evolution. Another valuable insight comes from considering what these objects lack. The absence of certain volatile compounds, for instance, might indicate formation around a star with a higher ultraviolet output, which would have stripped lighter molecules from the disk. A lack of complex organics might suggest a disk poor in carbon, or one where chemical reactions proceeded differently. These negative signatures are as important as positive ones, because they reveal the range of conditions under which planetary materials can form. Beyond composition and structure, the mere existence of objects like 3I Atlas tells astronomers about the dynamics of planetary systems. Ejecting material into interstellar space requires significant gravitational interactions, usually involving giant planets. The fact that so many ejected bodies exist suggests that massive planets are common across the galaxy, a conclusion that aligns with exoplanet surveys, but is now supported by physical evidence. In other words, every interstellar object is indirect proof that giant planet formation is not an anomaly, but a near-universal feature of planetary evolution. As the catalogue of known interstellar objects grows, patterns will emerge. Scientists will be able to group them by composition, density, structure, and orbital behavior, gradually building a taxonomy of extrasolar debris. This classification will, in turn, shed light on the range of planetary systems that exist, their architectures, chemistries, and histories. And because these objects are not limited to the planets we can detect via transits or radial velocity, they offer insights into systems too distant, too dim, or too small for current methods to study. In the end, 3I Atlas and its companions are not just messengers from other star systems, they are tools for decoding them. They provide direct, physical evidence of how worlds are built and destroyed, how chemical environments differ across the galaxy, and how the processes that shaped our solar system play out elsewhere. Each one is a fragment of a cosmic puzzle scattered across light years. And with every new piece that enters our sky, the picture of the galaxy's planetary diversity becomes a little clearer. Even the definition of what belongs to the solar system becomes more complicated under this new view. Does a comet captured from another star billions of years ago belong to us now? What about material that formed here but now orbits another star? The traditional boundaries that once defined planetary science, the heliosphere, the Kuiper belt, the gravitational influence of the Sun, still have meaning, but they no longer tell the whole story. The solar system is not a box, it is a crossroads. This recognition also changes how scientists approach the search for life. If planetary systems routinely exchange material, including organics and possibly microbes, then life's origins might not be strictly local. It may be the result of galactic-scale processes, with key ingredients arriving from far beyond a planet's home star. Earth's water, for example, may have been delivered by comets or asteroids originating in other parts of the protoplanetary disk. Some of those bodies, in turn, may have been influenced by material from older stars. Life itself could be the product of chemical building blocks forged elsewhere and delivered here by forces we are only beginning to understand. The recognition of a more porous solar system also influences how scientists think about planetary defense and exploration. If interstellar objects are far more common than previously believed, they represent both potential risks and opportunities. Large objects traveling on hyperbolic paths could, in theory, pose impact threats that differ from those of solar system asteroids, requiring new detection and mitigation strategies. At the same time, their predictable arrival patterns could provide opportunities for sample return missions or even human exploration. This new understanding also encourages a shift in language. Instead of thinking of the solar system as a place, it is increasingly useful to think of it as a region of flow, a gravitational eddy in a larger galactic current. In this model, the Sun and planets are relatively stable features, but the space between them is dynamic, filled with a constant movement of dust, rock, and ice. The system has shores, but its waters are never still. 3I divided by Atlas is a visible reminder of that reality. It is not an alien invader from beyond, but part of a process that has been shaping the solar system since its birth. It illustrates that the solar system's history cannot be told in isolation from the galaxies, because the two are inseparable. What we once thought of as ours is in many ways shared the product of interactions, exchanges, and collisions on a galactic scale. And as more interstellar objects pass through and more evidence accumulates, that new picture will only grow clearer. In that sense, 3I Atlas has done more than expand our catalogue of known objects. It has expanded the very idea of what a planetary system is. It has shown that our solar system is not a self-contained chapter in the universe's story. It is a paragraph in a much larger narrative, one that stretches across the spiral arms of the Milky Way and binds distant worlds together in ways we are only beginning to comprehend. A new era of observation. The discovery of 3I Atlas and the revelation that it is not alone have done more than expand our scientific curiosity. They have triggered a fundamental transformation in how astronomy is practiced. For centuries, astronomy was an observational science focused on light, the glow of distant stars, the spectra of nebulae, the faint signatures of exoplanets transiting across suns. But interstellar objects have introduced something radically different into the field. Physical, tangible samples from other star systems passing right through our cosmic backyard. This shift is forcing astronomers to rethink how they search the skies, how they design instruments, and how they plan missions. The first change is already underway in how the sky is surveyed. Traditional near-Earth object (NEO) searches were never optimized for high-speed, hyperbolic visitors. ʻOumuamua was discovered by accident, its fast trajectory almost overlooked because survey algorithms were tuned to detect objects bound to the Sunday. Borisov was easier to spot, but still required careful follow-up to confirm its origin. Now, with the knowledge that multiple interstellar objects may pass through the solar system each decade, survey strategies are being rewritten. Algorithms are being trained to recognize unusual motion patterns, deeper searches are being run at greater distances, and detection thresholds are being lowered to catch objects much earlier in their inbound trajectories. Future observatories will go even further. The Vera-C, Rubin Observatory's legacy survey of space and time, will be able to scan the entire visible sky every few nights, capturing faint objects months before they approach the inner solar system. Space-based instruments, like NASA's planned NEO-Surveyor, will search from above Earth's atmosphere, detecting infrared signatures of small, cold objects long before they reflect enough sunlight to be seen. Together, these systems will turn the detection of interstellar visitors from a rare event into a routine occurrence. Once these objects are detected, the focus shifts to rapid characterization. Because interstellar visitors move quickly and are visible for only a limited time, follow-up observations must be coordinated within hours, not weeks. This requires a level of global collaboration that astronomy has rarely needed before. Networks of ground-based telescopes are being linked into automated alert systems, allowing observatories on opposite sides of the planet to hand off targets as they move across the sky. Robotic telescopes capable of instant response are being developed to gather spectroscopy, photometry, and polarization data before the object fades from view. Space-based platforms are also playing a growing role. The James Webb Space Telescope, with its sensitive infrared instruments, can detect faint volatiles and organic molecules from great distances. The European Space Agency's Gaia mission is refining orbital data with unprecedented precision, allowing scientists to trace trajectories backward into interstellar space. Future missions may include dedicated interstellar object observatories, spacecraft stationed at strategic points in the solar system to detect, track, and analyze incoming visitors far beyond Earth's orbit. Perhaps the most dramatic change lies in how scientists think about missions. Until recently, space missions were planned decades in advance, with carefully chosen targets and long preparation timelines. Interstellar objects have upended that model. Their unpredictable arrival times and brief visibility windows demand rapid, flexible responses. Engineers are now exploring modular spacecraft designs that can be built and launched within months, not years. Some concepts envision pre-deployed interceptors waiting in deep space, ready to redirect toward a target at a moment's notice. Others propose fleets of small, inexpensive probes capable of dispersing across multiple trajectories to increase the chances of a successful flyby. The growing interest in interstellar objects is also influencing how data is shared and analyzed. Because these objects cross multiple research domains, planetary science, astrophysics, astrochemistry, and even astrobiology collaboration is essential. International working groups now coordinate observation campaigns, pool resources, and share real-time data across borders and institutions. The result is a more agile, interconnected scientific community, one capable of responding quickly to rare events and extracting as much information as possible from them. This transformation is about more than just adapting to a new class of objects. It is about recognizing that the universe is more dynamic than once thought. Instead of being passive observers of distant stars, astronomers are now studying material that comes to them. Instead of relying solely on light, they are preparing to analyze dust, gas, and rock from other solar systems. And instead of thinking of planetary science as something confined to our own star's domain, they are beginning to see it as part of a larger galactic context. The new era of observation sparked by 3I Atlas and its kin will change astronomy in ways that go beyond science. It will demand faster decisions, more flexible missions, and deeper cooperation than ever before. It will push technology toward higher speeds, sharper sensors, and broader coverage. And it will give humanity something it has never had before: a continuous, physical connection to the wider galaxy, carried by the silent travelers that pass through our skies. Each one will be a fleeting opportunity, but together they will rewrite our understanding of how planetary systems form, evolve, and connect across the Milky Way. A new kind of astronomy. The emergence of 3I Atlas and the discovery that it is accompanied by other interstellar objects have done more than expand humanity's knowledge of the universe. They have redefined what it means to study it. Astronomy, once a discipline built on passive observation of light from distant stars, galaxies, and nebulae, is becoming something more tactile and immediate. For the first time in history, material from other planetary systems is not just visible in the night sky. It is physically entering our solar system, offering direct evidence about environments we cannot yet reach. This shift is transforming both the goals and the methods of modern astronomy. For centuries, astronomers relied on photons as their only source of information. Light revealed the composition of stars, the movement of galaxies, and the structure of the cosmos. But it was always indirect, an interpretation of signals that had traveled vast distances. Interstellar objects change that. They are not just signals, they are samples. They carry with them atoms, molecules, isotopes, and minerals, forged in conditions different from those of our Sun's system. By studying them, scientists can test theories of planet formation, stellar chemistry, and galactic evolution, with physical evidence rather than inference, evolution with physical evidence rather than inference. This new era demands new approaches. Traditional telescopes and surveys are still essential, but they are now part of a broader toolkit. Astronomers must integrate spectroscopy, dynamical modeling, radar imaging, and laboratory analysis into a unified framework. The field increasingly overlaps with planetary science, astrochemistry, and astrobiology, drawing insights from each to interpret the data these objects bring. When 3I Atlas releases volatile gases near perihelion, for example, chemists can analyze their spectral signatures to infer formation temperatures. When fragments of a captured interstellar object are studied in a laboratory, mineralogists can trace their crystalline structure to conditions that existed millions of years ago in another star's disk. Interdisciplinary collaboration is becoming the norm rather than the exception. Teams now include not just astronomers, but geochemists, computational physicists, organic chemists, and spacecraft engineers. The discovery of ʻOumuamua in 2017 was studied primarily by astrophysicists. By contrast, 3I Atlas is being examined by scientists across multiple fields, each asking different questions. What does its chemical profile tell us about protoplanetary disk chemistry? What do its trajectory and velocity reveal about the distribution of small bodies in the galaxy? How does its surface weathering inform our understanding of radiation exposure over millions of years in deep space? This shift is mirrored in how astronomical infrastructure is designed. Future observatories are no longer planned solely with stars and galaxies in mind. They are being built to track small, faint, fast-moving objects across vast portions of the sky. Spacecraft are being designed not just to orbit planets or study the sun, but to intercept and sample objects on hyperbolic trajectories. Laboratory facilities are being prepared to handle materials with isotopic compositions and chemical signatures unlike anything found in the solar system. The discipline is expanding beyond observation into direct interaction with material from beyond. The impact of this transformation extends beyond science. It changes humanity's relationship with the galaxy. For most of history, the stars were distant and unreachable, their stories written in light we could only interpret from afar. Now, fragments of those distant worlds are arriving on our doorstep. They are no longer abstract, they are physical, measurable, and real. And in their arrival, they collapse the distance between here and out there. The galaxy is not just something we look at, it is something that piece by piece comes to us. This new kind of astronomy also challenges the notion of time. Observing distant galaxies allows us to look billions of years into the past, but studying interstellar objects lets us hold pieces of that past in our hands. A fragment of ice from 3I Atlas might contain molecules that formed before Earth existed. A grain of dust trapped inside it might have condensed around a red dwarf star in the early Milky Way. These are not just clues to other worlds, they are physical records of the galaxy's history, delivered across time and space. The story of 3I Atlas, then, is not just about a single object, or even a class of objects. It is about a turning point in how humanity studies the universe. We are moving from an era of passive observation into one of active investigation, from watching the cosmos to engaging with it directly. As more interstellar visitors are discovered, and as technology advances to meet them, astronomy will continue to evolve into something broader, deeper, and more interconnected. The galaxy is no longer a distant spectacle. It is a landscape we are beginning to explore, piece by piece, carried to us by the silent messengers that drift across the space between stars. The messengers keep coming. When ʻOumuamua was first spotted in 2017, many astronomers assumed it would be a once-in-a-generation discovery, a cosmic accident we might not see again for centuries. That assumption has not survived the last few years. In less than a decade, humanity has gone from knowing of no interstellar visitors to studying several, and evidence now suggests there could be thousands passing through our solar system every year, most too faint for us to notice. The lesson is clear. 3I Atlas is not an isolated event. It is part of a steady, ongoing phenomenon that will shape planetary science for decades to come. The realization of just how many objects might be out there began with statistical modeling. If ʻOumuamua and Borisov were both detected within a short span of time, despite the limited sensitivity of existing surveys, then logic dictates that many more must have slipped past undetected. As telescope sensitivity improves and sky surveys become more comprehensive, that hidden population is starting to reveal itself. 3I Atlas and the companion objects discovered in 2025 are likely only the first members of a much larger group, and they are changing how scientists think about the solar system's place in the galaxy. Some researchers now believe that small interstellar bodies could be passing through the solar system on a weekly or even daily basis. Most are likely just a few meters across, far too small to detect with current instruments, but larger ones, tens or hundreds of meters wide, may be appearing far more frequently than anyone realized. These are not catastrophic events or rare coincidences. They are the steady background traffic of the galaxy, fragments of planets and comets scattered by gravitational encounters millions or billions of years ago, and now quietly drifting past our star. This growing realization is prompting astronomers to treat interstellar objects not as special cases, but as a fundamental part of the solar system's environment. Just as Earth encounters meteor showers as it crosses streams of debris from old comets, the solar system itself appears to move through a galactic field of small bodies. Over cosmic timescales, this field changes as stars migrate, spiral arms rotate, and stellar clusters disperse. At some points in its orbit around the Milky Way, the Sun may encounter relatively dense regions filled with ejected material. At others, it may drift through quieter zones. The recent increase in detections could reflect not just better technology, but also the solar system's current passage through a debris-rich region of space. The implications are profound. If the solar system regularly encounters interstellar material, then its influence on planetary evolution may be far greater than previously thought. Ancient impacts by interstellar bodies might have delivered exotic materials to Earth and the other planets' metals, volatiles, or even organic compounds formed around distant stars. Some of these impacts might have left detectable chemical signatures buried deep in planetary crusts or preserved in ancient meteorites. The steady infall of such material could even play a subtle role in shaping planetary atmospheres and surface chemistry over geological time. This new perspective also changes how scientists plan for the future. Rather than waiting for rare opportunities, astronomers are preparing for a future in which interstellar encounters are routine. Future surveys will not only search for near-Earth objects, but also catalogue and characterize the continuous flow of extrasolar debris. Spacecraft may one day be stationed at strategic points throughout the solar system, ready to intercept objects as they approach. And sample return missions could become a regular part of planetary science, retrieving fragments of other worlds as they pass within reach. The growing awareness of how common these visitors are is also reshaping our understanding of the galaxy itself. Every interstellar object is a messenger from another planetary system, carrying physical evidence of its history. If thousands of such objects pass through the solar system each year, then thousands of planetary systems are leaving traces here, each one a clue to the galaxy's diversity and complexity. By studying them, we can learn not just about individual stars, but about the broader processes that shape the Milky Way, from star formation and planetary migration to chemical evolution and the distribution of organic molecules. And this is likely only the beginning. The number of known interstellar objects will almost certainly grow as detection methods improve. And with each new discovery, our picture of the galaxy will become more detailed. We will learn how often planets eject material, how that material evolves in interstellar space, and how it interacts with other systems when it arrives. Most importantly, we will learn how our solar system fits into that larger picture, not as an isolated anomaly, but as one node in a vast galactic network of matter and memory. The story that began with a single mysterious object in 2017 has become something much larger. The messengers keep coming, and each one carries a piece of a story written far beyond the reach of our spacecraft or telescopes. Together, they reveal a galaxy alive with movement, a galaxy where worlds are not just places, but participants in a shared, ongoing exchange that has been unfolding for billions of years and will continue long after we are gone. The story of 3I Atlas is not ending, it's just beginning. With every new detection, the old idea of a sealed-off solar system fades further into memory, replaced by a deeper truth. Our star is part of a vast network, exchanging matter, chemistry, and maybe even the seeds of life with countless others. These objects are not visitors, they are threads in a cosmic tapestry, passing silently through our skies to remind us that the galaxy is alive with movement. And if we keep watching, if we build the tools to meet them halfway, they will show us more than we ever thought possible. If you want to follow that story, the discoveries, the missions, the next messenger, already on its way, make sure you're subscribed. There is so much more out there, and every fragment that crosses our sky is a piece of the universe's memory.